familiar with this law, the total magnetic field, ठीक है, is in the Ampere's loop जो है, it is basically equal to the total current enclosed by that loop here. So in order to understand this this concept, just consider that we have the three wires here, I1, I2, and that of I3. So these wires carrying the current here, I1 is out of the paper while I2 is into the paper, I3 is out of the paper. So we have taken a randomly Amperian loop. So this is the Amperian loop with the orange line here. ठीक है, बेटा आवाज आ रही है आपको?
एक्सक्यूज मी सर।
जी जी
सर, रिकॉर्डिंग्स तो आपने अपलोड की हैं, लेकिन सर बीच में उनमें काफी मतलब क्या लें मिसिंग्स हैं।
बेटा मिसिंग इन व्हाट सेंस बेटा?
रिकॉर्डिंग्स मतलब कुछ नहीं है।
मैंने तो बेटा सारी अपलोड की एक्सेप्ट वन, एक रिकॉर्डिंग के विच आई अनफॉर्चुनेटली क्या थे उस दिन मैं रिकॉर्डिंग कर नहीं था सका, ठीक है। सो अदर देन दैट मैंने तो सारी बाय डेट्स जो हैं वो आई हैव अपलोडेड ऑल द लेक्चर्स, ठीक है। आप मुझे डेट्स बता दें, देन आई विल लुक इनटू इट, ठीक है, कि कौन सी डेट्स की नहीं है, तो देन आई विल लेट यू नो, ठीक है, ठीक है। बिकॉज देयर इज अ सीक्वेंस बिटवीन द रिकॉर्डिंग्स के you can compare it with the lectures, ठीक है। Let's suppose yesterday we studied Boyd-Sauer's law, so it means that Boyd-Sauer's law should be present. So if Ampere's law is not present, so this recording is missing. So you can tell me, sir, okay sir, the recording of the Boyd-Sauer law is present, but the recording after that of the Ampere's law is not present. So then I will upload it again, okay. So in I think that I have uploaded all the lectures, but just let me know, state that if there is if any lecture is missing, just let me know, and then I will upload it again, except one lecture which I do remember that I missed because I didn't record that lecture, ठीक है।
ओके सर, अगर मैं आपको डेट्स बता दूंगा जो मिसिंग है।
ठीक है बेटा, ठीक है, फाइन। ओके, सो this is the Amperian loop here. So we have taken the Amperian loop between which encloses only two wires here, okay, not the third one, okay. So we want to find out the magnetic field. So the basic principle you should always remember that when you have an Amperian loop and there is a wire that is out of the Amperian loop, you cannot find out the magnetic field. The reason is this law clearly says that you will be able to find out the magnetic field only only for the enclosed current. So the enclosed current here is I1 and I2. I3 is out of the loop, so we cannot find out the magnetic field. Again, the reason for this one is that these two have the magnetic fields that are that is within the loop here. So this I3, ठीक है, also have the magnetic field, but if we will consider that this magnetic field is in the circular form, ठीक है, so what will happen that the number of the magnetic field lines entering the loop is equal to the magnetic field lines getting out of the loop. So basically they are cancelling out each other, so there will be no net magnetic field inside the Amperian loop due to the I3. So that's why we will only consider those currents that are enclosed by the Amperian loop. Is it clear, beta?
Sir, you kindly repeat करने हैं, clear नहीं हुआ।
अच्छा, always remember that as per Ampere's law, you will be able to get the magnetic field only for those currents that are enclosed by the Amperian loop. So how many currents are enclosed by the Amperian loop in this example? I1 and I2, while I3 is out of the Amperian loop. So we cannot find out the magnetic field. Okay, the question comes to mind, okay, I3 also have the magnetic field because it is the current carrying wire, so it should have the magnetic field. Obviously it has the magnetic field, but the problem is that it will create no impact within the Amperian loop, because let's suppose what would be the direction of the magnetic field? It will be in the surrounding, okay. So number of lines will be like in circular path like this one, okay, in the circular form. So the number of lines entering will be is equal to the number of lines getting out of the Amperian loop. So as a result, what is happening here, that there will be no magnetic field, okay, inside the Amperian loop, because they are basically cancelling out each other. Okay, magnetic field lines due to the I3 entering into the Amperian loop is also getting out of the Amperian loop, so they are basically cancelling out. So the only magnetic field lines that are creating the magnetic field within the Amperian loop is due to the I1 and I2. Now it is clear to you, beta?
Yes, sir.
Okay, so just like the Gaussian loop, yeah, Gaussian surface, we will divide this Amperian loop into the smaller differential elements. Okay, and here we have taken this element like ds, we have divided the loop ds. ठीक है, और क्या होगा कि the direction of the magnetic field will be tangent to the Amperian loop at any point. ठीक है, you can see here that the circular form will always be tangent to the Amperian loop. ठीक है, at each and every point in this scenario. ठीक है, because they are in circular form here. And the direction of the arrow we have taken. ठीक है, अब आप मेरे से पूछ सकते हैं why we have taken the arrow in the counterclockwise direction, why we have not taken it in the clockwise direction. So it is the random direction. ठीक है, it is the random direction, we take it at the start. It basically shows the direction of the integration. ठीक है, so it can be clockwise, it can be anti-clockwise. So let's suppose if you are later on you will see that if you are getting the positive answer, it means that the direction is fine. If you are getting the negative answer, it means that the direction of the integration is wrong. So then we will take the direction in the opposite side. ठीक है, ये चीज समझ में आ गई बेटा? चलें, मूविंग टुवर्ड द नेक्स्ट स्टेप. ठीक है, लेटर ऑन आपको बताएंगे कि थंब रूल क्या है, कि हाउ यू विल बी एबल टू फाइंड आउट द डायरेक्शन ऑफ द इंटीग्रेशन. बल्कि मैं पहले बता देता हूं,
ये जो इक्वेशन 29.14 है, मैग्नेटिक फील्ड बी से पहले ये जो साइन दिया हुआ है सर, ये क्या चीज है? मतलब
इंटीग्रल के ऊपर बेटा एक क्लोज लूप है. सर्कल मींस इंटीग्रल के ऊपर क्लोज लूप है. दिस एम्पीरियन लूप इज क्लोज्ड वन. ठीक है, क्लोज सरफेस के लिए. ठीक है, they also mentioned it a closed loop. ठीक है, so since we are taking the closed Amperian loop, so obviously it is a closed surface. ठीक है, so current in closed तभी होगा ना बेटा जब आपके पास closed surface होगी. ठीक है, अगर ये closed surface ना हो तो it means के I3 तो included होगा फिर. तो enclosed current तो उसी वक्त हो सकता है कि जब आपने एक box liya and there are two wires inside the box and there is one wire outside the box. So how many wires a box has? Obviously you will say that there are two wires inside the box because they are enclosed by the box, while the third wire is out of the box, so we cannot include that wire, okay, in the box. Now it is clear beta?
Yes.
ठीक है, so अब आ जाते हैं कि how we can differentiate direction of the integration. इंटीग्रेशन जो है कि what would be the direction of the integration, how we can consider that it is positive or it is the negative. So always consider that if you will take the fingers in the direction of the integration which is in the counterclockwise, and if thumb is in the upward direction it will be positive, if thumb is in the downward direction it will be negative. ठीक है, ये इन्होंने बताया हुआ है यहाँ पे भी. ठीक हो गया. अब आ जाते हैं कि we will divide the this Ampere loop into the small elements. ठीक है, and when we will divide it into the small elements, ठीक है, ds was the small element. ठीक है, so the relation would be something like this one, b cos theta ds is equal to mu naught I enclosed. ठीक है, later on we will utilize this equation in order a straight wire and outside a straight wire and inside a straight wire. ठीक है, so ये सारी चीजें बेटा इसके अंदर एक्सप्लेन की हुई है and there is nothing that would be difficult for you. ठीक है, Now here कहता है कि if B turns out, which I told you earlier, if B turns out positive, then the direction we assume is correct. If the B turns out negative, then the direction we assume is the wrong one, and then we will draw it in the opposite direction. So here the total current enclosed by the loop was I1 minus I2. So the relation will become I enclosed was equal to I1 minus I2. So the B cos theta D is equal to mu naught I1 minus I2. Clear है बेटा? Any question? Any confusion बेटा? You can ask me right now.
सर एक बच्चा वेट कर रहा है, उसको इंटर करते हैं.
Okay, एक मिनट बेटा, एक सेकंड. So any question बेटा up to this point?
सर ये यहाँ पे
Okay. Basically it was B dot ds. So B dot ds will give you B cos theta, B ds cos theta. ठीक है? Scalar product है यहाँ पे between the magnetic field and that of the ds. ठीक है? ये आप देखें ना in this figure. This is the angle here, B and that of the ds. ठीक है? Green color is representing the B dot ds. So B ds is equal to B dot ds is equal to B ds cos q. Clear? Cross product है. Any other question बेटा? चलो fine. अच्छा फिर आ जाते हैं कि in this paragraph he basically asked for why we are not taking the I3, which I told you earlier because क्या होता है कि number of magnetic field lines entering and coming out of the loop, they will cancel out each other. This is what they have written here. Magnetic field will cancel out. ठीक है? तो ये चीज है बेटा यहाँ पे. अब आ जाते हैं कि we want to find magnetic field outside a long straight wire. ठीक है? We will use the Ampere's law. ठीक है? और we want to find out के what would be the strength of the magnetic field due to this long straight wire. So in the Boyd-Savart's law, we calculated it, and the strength was for the magnetic field outside a straight wire was equal to mu naught I over 2 pi r. So we will see that whether Ampere's law will give us the same answer or it will give us the different answer.
वो length पे depend करेगी ना?
लेंथ पे ही करेगी उसकी सराउंडिंग में ना. तो लेट्स सपोज कि हम लोग करते हैं हमारे पास स्ट्रेट वायर में सर्कुलर फॉर्म में, तो क्या आएगा हमारे पास एट ए डिस्टेंस. वो बेसिकली करती है कि आपका डिस्टेंस कितना है वहां से, स्ट्रेंथ ऑफ द करंट पे, हाउ मच करंट इज फ्लोइंग म्यू नॉट आई ओवर 2 पाई आर मींस दैट इट इज डायरेक्टली डिपेंडेंट ऑन द करंट. ठीक है? एंड इनवर्सली डिपेंडेंट अपॉन द डिस्टेंस फ्रॉम द वायर. ठीक है?
जी सर.
ओके. अब आ जाते हैं कि नो दिस इज द वायर, current is coming out of the paper. ठीक है? और we have drawn a Amperian loop in this surrounding. So Amperian loop, when we have drawn the Amperian loop around the circular wire, we have taken the Amperian loop in a form of circle. So this circle is here. ठीक है? So we have divided this Amperian loop into small element ds. So one element is given by here at this point. This is the ds. Also, since the magnetic field is in the circular form around the wire, so we have taken the Amperian loop in the circular form. So the magnetic field at each and every point will be tangent to the surface. ठीक है? यही नहीं होगा? At each and every point, the direction of magnetic field will be along the tangent of the surface. यही होगा?
सर रिपीट कीजिएगा.
Magnetic field exists in a circular form. यही होता है ना straight wire के लिए.
Yes sir.
Current pass हो रहा हो, तो magnetic field in the surrounding of the wire exists in the circular form. ठीक है? So since we are taking the Amperian loop in a form of circle, so magnetic field is also circle. So the direction of magnetic field at each and every point will be tangent to the surface. B होगा ना, tangent to the surface means के the tangent of the circle ये है ना, it will always be like this one, tangent of the circle. So it means कि क्या होगा कि आपके पास ds or the magnetic field, the angle between them will always be zero because both are parallel to each other. Since magnetic field is tangent to the surface, so it is parallel to the front length element. So the angle between B and ds would be equal to zero. So it means that B ds cos theta would be equal to B ds cos zero, or it will be equal to B ds. ठीक है. So अब हम लोग आगे चलते हैं in the next step कि this is what they have mentioned here. Angle between the B and ds is equal to 0 degree. So cos theta will be equal to cos 1. So B cos theta ds will be equal to B ds, while B is constant. So the only variable thing we have the ds element because we have divided the into Amperian loop into the small elements, differential elements. Now we will integrate it. When we will integrate it, so what was the circumference of the Amperian loop? It was क्या था, pure circle था. So circumference of the circle would be 2 pi r. यही नहीं होगा, 2 pi r नहीं होगा बेटा?
Yes, sir.
ये देखे ना, ये Amperian loop is in the circle है. So magnetic, we are finding out the magnetic field. So we have divided the circle into the smaller elements. So when हमने circle को small elements में divide किया, and when we have integrated them in order or sum them in order to get the full length of the Amperian loop, so it will be equal to 2 pi r. ठीक है? S is equal to 2 pi r. ठीक है? So B 2 pi r would be equal to mu naught I. ठीक है? और आपके पास B would be equal to mu naught I over 2 pi r. So this is the magnetic field outside the straight wire, and this is the same answer which we got from the derivation of Boyd-Savart's law. Clear हो गया? Any question up to this point, बेटा?
No, sir.
चले, अब आ जाते हैं toward inside the wire. ठीक है? ये छोटा सा आर्टिकल.
सर एक मिनट रुकिएगा.
जी जी. आपकी क्लास है आगे बेटा?
जी सर.
अच्छा, जस्ट गिव मी 10 मिनट्स मिल जाएंगे मुझे. अब कहता है कि नो, पहले हम लोगों ने क्या किया था, वी हैव टेकन द मैग्नेटिक फील्ड आउटसाइड द वायर, एंड नाउ व्हाट वी आर डूइंग इज दैट वी वांट टू फाइंड आउट द मैग्नेटिक फील्ड इनसाइड द वायर. सो अगेन हम लोग क्या करेंगे कि now we will take the Amperian loop inside the wire. ठीक है? So this is the Amperian loop inside the wire, and this is the outer surface of the wire. So the radius of the wire is capital R, while the radius of the Amperian loop is small r. So it means that small r is less than to the capital R, meaning that Amperian loop has a radius smaller than the radius of the wire. So in this way, we will be able to find out the magnetic field inside the wire here. Again, you can see here that when we will divide the Amperian loop into the smaller portions into differential elements, so ds will be parallel to that of the B here. So B dot ds or B ds cos theta will be equal to B ds. ठीक है? In the same way like here we have done this. So this would be equal to what? B 2 pi r. ठीक है? This is the thing which we got here. The only thing, ठीक है, which is different here is enclosed current. Now we want to find out the enclosed current. So since the wire, he clearly mentioned that the current is uniformly distributed. Current is uniformly distributed means that it has the uniform current density. This is what mentioned here. The whole wire here has the uniform current density. Current density means that current per unit area in this whole, let's suppose this is the wire, and this whole wire is same. current per unit area in this whole wire is same. So if I will divide this whole wire into small elements, ठीक है, let's suppose I am dividing it into these small segments. So the current density or the current per unit area will be same. क्या same होगा कि नहीं होगा? Whole, I am taking the whole wire and then I am taking the smaller portion of the wire. So current density should be same or not?
सर अगर करंट सेम है तो डेंसिटी भी सेम होनी चाहिए. करंट
डेंसिटी सेम है, ठीक है. There is a total wire, current I is passing through the whole wire. So when I am dividing it, तो current density कम नहीं हो जानी चाहिए कि सेम रहनी चाहिए?
Divided areas में तो पर एरिया वो बराबर आती है.
Obviously, the thing is कि if I am taking the current density किसके बराबर होती है? J is equal to I by A, ठीक है. So when I am taking the whole wire, it means that I am taking the total current, ठीक है. तो total current अगर मैं ले रहा हूँ 1 ampere, ठीक है, and then I am taking the total area 2, ठीक है. total area जो है 2 सेंटीमीटर स्क्वायर का, ठीक है. तो क्या होगा? Obviously जो भी है 1 divided by 2 current density would be equal to what? क्या आएगा जी? 1 divided by 2 क्या आएगा? करंट डेंसिटी क्या आएगी जी? 0.5 आ जाएगी. On the other end, when I am taking the smaller portions, no doubt the value of current is getting smaller. Let's suppose I am taking half value, ठीक है. अगर मैं half value ले रहा हूँ तो करंट की 0.5 ले रहा हूँ, but also what is happening that I am also dividing the area too. अगर मैंने half wire ली है तो I am getting half area too. So it means कि half area क्या मेरे पास now 1 है. What is the final answer? 0.5. In both cases, now you are getting the same current density value. So if it means that if you are dividing the wire and if you are taking the total wire, if current is uniformly distributed, so current density will remain same whether you are taking the half portion of the wire or you are taking the full portion of the wire. No, is it clear to you बेटा? ये चीज समझ में आ गई आपको?
सेम रहेगी.
ये चीज समझ में आ गई. कंडीशन क्या है? that it should be uniformly distributed, ठीक है. ये कंडीशन है. ये ना हो कि किसी जगह पे चार्जेस ज्यादा हो, किसी जगह पे चार्जेस कम हो, then obviously answer will not be same. But if it is uniformly distributed, then current density will always be same. So remember this portion, remember this part here. We will utilize this part. So this is what he is doing here. कहता है कि to find, अब ये obviously हम लोगों ने integral part तो calculate कर लिया, ठीक है. So what will be the value of the I enclosed current? अब problem क्या है कि this is the wire here, ठीक है. So the total current it has I, but the Amperian loop has a distance smaller, ठीक है. ये smaller